Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 42. As the subject is of the continuation, so for the convenience, the link of the previous one is given under the description box. Let's start with condition monitoring of the on-load tap changers. At the present context of distributed energy systems, sustainability and stability in voltage regulation would have become the prime significance of operational concept in case of on-load tap changing transformers. The on-load tap changer consists of a high-speed resistor transition diverter switch, tap selector, driving mechanism, and external driving shaft. From failure statistics, it has been exhibited that more than 27% of the total number of transformer failures are caused by imperfect or erroneous operation of OLTCs. The relative contribution of tap changer failure that has to justify appropriate measures to timely identify and mitigate tap changer defects. Predominant failure mechanisms of tap changers. Number one, loss of stability in mechanical system mechanism. Number two, defects in current carrying mechanism. And number three, deterioration in insulation mechanism. The first one, loss of stability in mechanical system mechanism, which is due to worn out spring energy accumulator system that creates problem to operate diverter switch. Number two, defects in the bevel gear and worm gear assembly. And the last one, problem in external drive shaft coupled with motor drive mechanism. Defects in current carrying mechanism consist of two categories. One is contacts of tap selectors and transfer switch are subject to degradation due to discharges or friction. And second one, problem arises in transition resistor track mechanism. The last one, deterioration in insulation mechanism. Degradation of oil insulation due to long-term switching effect and major insulation defects in star and delta connection connected OLTCs. Now, see some salient points. Number one, as of the older version, the active transformer parts and the tap changer, including the tap contacts and the switches all together, may have to share the same oil compartment. That is, everything is in the same oil compartment. However, in order to prevent pollution of the entire transformer oil by means of tap changer contaminants and vice versa, the tap changer is thereby placed in a separate oil compartment. Number three, to assist in arc interruption process. Hence, the on-load tap changer oil from diverter switch housing and selector switch housing would have the possibility to depreciate due to the gathering of suspended carbon particles as well as formation of sludge. Number 4, modern designs of the diverter switch type tap changer in which oil is totally replaced by the process of vacuum switching technology, where arcing interruption is nicely achieved in hermetically sealed chamber. The latest version is the modern design concept. Reasons for operational limitations of OLTC. On-load tap changer, as it is being configured with large number of moving parts, so it must have to operate in a precise fashion in order to maintain a constant voltage output. Therefore, OLTC would have been the most important as well as critically vulnerable part of the transformer, as it tends to deteriorate over time due to mechanical problems or contact wear from repeated operation. Tap changer has to move from one tap to another, and there have to provide diverter resistors for the currents, where diverter contacts are required to break and make at the duration of a tap change. The selector switch first selects the desired tap to switch. Later, the diverter switch performs the transfer of load current from one tap to the other. It's a process. During operation, the switching contacts are always be subjected to a high load current while the OLTC is in the transition phase from one tap position to another. This would eventually lead to a considerable decrease in the conductivity of the contacts, and that may cause damage to these contacts. However, any sort of damage to switching contacts and other interrelated components can cause the OLTC to malfunction and may have to fail, which ultimately diminishing the transformer's reliability. Operational performance is thus to be broadly entertained into the designed switching time and lifetime switching time, as so far been prevailed. Again, I repeat, operational performance is thus to be broadly entertained into the design switching time and lifetime switching time, as so far been prevailed. As the OLTC is configured with critically built numerous moving parts, so there would have been recommended for establishing a robust maintenance cycle that mostly has to depend on the total number of switching operations. With the role of capturing data, life cycle of the OLTC can have to be systematically assessed through an integrated offline and online condition monitoring techniques. Based on its working mechanism and structural configuration, certain limitations there have to be implied for the following technical findings as exhibited. 1. Over time, erosion of contacts of the tap selectors and the transfer switch due to discharges and friction would have been the obvious criteria, as due to the nature of their function. Coking of the contacts. Coking of the contacts as being caused from the subsequent process of carbonized oil film formation would have been resulted severe overheating. excessive coking may have to instigate a thermal runaway of the contact and diverter switch materials as because of increased contact resistance. After having thorough investigation of transformer oil chemistry, gas evolution, contact performance under the conditions of accelerated switching operations, focused on stationary reversing switch assemblies and diverter switch contacts, it has been concluded that the concern of coking is mostly solved by using silver plated contacts. The study also suggests that tungsten copper composites, tungsten copper composites are specially good for making the arcing contacts in high voltage application. Transition resistance in OLTC is one of the most significant as well as critical component because it affects the voltage and current conduction. Transition resistance in OLTC is a device that has to provide two groups of transition resistors of identical parameters which are fixed on a left and right mounting buttons through bolts. The main objective of using resistor in the OLTC as arranged in series with the tapped winding is to maintain the voltage by controlling the flow of current using switches. The resistive element that has to limit the circulating current when the taps are in the bridging position, causing a short circuit across the incoming section of tap winding. Number 10, the tap selector is first to select the tapping whose electrical contacts are used to carry the nominal current of the transformer. During the current breaking and making process, there would have been an arcing at all the fixed contacts. This has resulted contact erosion in the diverter unit as well as would cause oil contamination of the diverter unit chamber. Number 13, the transition resistors would also have to entertain excessive conduction losses, which might have been lead to burning of transition resistance. Conduction losses are simply the product of the current flowing through the switching contact while at its turned on transition and the voltage drop across it. The problem is thus to determine the actual voltage drop is at any given time because this has to vary with temperature and current. So, operational reliability of OLTC can be ensured only by means of optimizing the process of maintenance through a systematic interpretation of condition monitoring system. However, condition monitoring system should be framed by having judicially adjudged the basic consequences from the major troubleshooting scheme as configured by the operational as well as maintenance wing. Condition-based maintenance, that is CBM, or predictive maintenance, that is PM, that has to be integrated through condition monitoring strategies by implementing additional monitoring sensors, circuitry, and control system. Through these additional monitoring sensors, the fundamental reasons for the failure must have to locate first. Then it has become much easier to implement an excellent fault diagnosis system. The concept of corrective maintenance should have to be undertaken in accordance with the types of defects as stated. Time-based maintenance is so far been prescribed as a common schedule that's to be carried out in every 3 to 5 years depending on the OLTC technology and connection. Condition-based maintenance, which aims to have the condition assessment of the tap changer through diagnostic tools that leads to a decision about the appropriate maintenance technology. Eventually, condition-based maintenance instead of time-based maintenance is found to be much more cost-effective as well as systematic outage of the important equipment like a transformer. Troubleshooting for implementing condition monitoring strategies. 1. A high-speed resistive type OLTC that has to provide a resistor pair to absorb energy and never be used the bridging position as a service position. In this type of operation, the change from one tap to another tap must be made quickly to avoid overheating of the diverter circuit. Number 3, the operating mechanism for most of the on-load tap changers is motor driven, but additional manual operation would always be provided in the event of motor failure. Number 4, the sequence of operation is mechanically interlocked so as to make it ensure that all of the contacts will always have to operate in their predetermined sequential order. Number 5, any failure or disruption of the operating mechanism would have been resulted in severe damage to the transformer and also the tap changer unit. Number 6, basically the tap changing winding can be designated as a variable linkage across a transformer circuit that allows a stepwise selection of a specific number of turns. The step voltage taps would have been configured in the range of 0.8% to 2.5% of the transformer's rated voltage. This is most important. The step voltage taps would have been configured in the range of 0.8% to 2.5% of the transformer's rated voltage. Selector switches and changeover selectors both are to be arranged that largely dependent upon the specific winding arrangements. Number 9, the selector switch that would have to act as the central control mechanism for making or breaking the current during the process of tap changing. The diverter switch would have to utilize in the circuit so as to effectively isolate certain portions of the selector's arm to propagate the tap changing process. However, the major features of the OLTC are mainly confined within a strategy of perfect sequence of switching process. Now, the switching process of OLTC must have a close relation with the arcing behavior in the context, which often may have to instigate a process of premature degradation of the insulation properties of oil in diverter's chamber, and also may lead to damage the winding insulation part of the transformer. The impact of the arcing issue can, however, be suitably mitigated by the implementation of vacuum switching technology or being shifted to an appropriate insulating switching medium technology. Monitoring schedule that must be chalked out with having due consideration of the designing arrangement of tap windings as implemented in the subject transformer. The designing arrangements of tap windings are as follows: A. Linear arrangement. B. Single course changeover selector. C. Multiple course changeover selectors. D. Single reversing changeover selector. E. Double reversing changeover selector, which is already explained as of the figure 131. For entertaining improved reliability and availability of OLTC, various maintenance schedules along with their periodicity and detailed procedure would have to be adapted during repair and overhauling. All essential aspects of maintenance of tap changer can be assigned by indicating the on-load tap changer problems such as contacts, mechanisms, energy accumulator, and motor problems. That is, driving motor problems. These are all being dynamic problems. And for the requisite analysis, that has to require perfect understanding with the principles of regulation and OLTC's cycle of operation. The performance and the possible defects of the tap changer should also be characterized through its speed, transition time, ripple, and other important features such as high temperatures, high load current, low contact pressure, material configuration of the contacts, etc. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.